Let's talk a little bit about calculation of area in 2D. This is very, very straightforward, obviously, because the areas of each control volume face essentially are lengths in 2D. So if you have a triangle, its face is going to look like that, just a line, segment, and therefore all you need to do is, so suppose I want to calculate the areas of all faces in my computational domain. Okay, so what I'm going to do is I'm going to run a loop over all the faces. So this loop IFC, that's the index, runs from 1 to n faces, which is the total number of faces. For each face, then I'm getting what are the two vertices, V1 and V2. Okay, that comes from the connectivity information that I have already stored, which is the face to node connectivity. Okay, so I give it the face index and I ask it for vertex 1 and vertex 2. That gives me these two numbers, and I can then use those two numbers to get the x coordinates and the y coordinates of those nodes or vertices. Okay, so this is just a distance formula, as you can see. Once I have the two coordinates, and then the area is nothing but that. Okay, so it's just calculation of a length, really. The only thing you need to understand is how to access all that information. Okay, and the information is accessed by using that connectivity data that we've already stored. So another example really of how to use the connectivity information. Any questions? So that's pretty straightforward. Let's talk about 3D now. In 3D, of course, you have a problem, and the problem is that if I have an arbitrary set of points, let's say, okay, now in 3D, of course, your control volume faces could be triangles, could be quadrilaterals, could be arbitrary polygons. Okay, now if I take any number of arbitrary points, okay, there is no guarantee that those points will lie on a plane. Okay, if I take 4 points, you cannot guarantee me that those 4 points will be on a plane. They could be just some warped surface. Okay, the only case where you can guarantee that is if you have a triangle. Okay, so a triangle always has a unique surface normal. A quadrilateral doesn't. It could be a warped quadrilateral in a sense. I shouldn't call it a quadrilateral, but 4 points joined by lines. Okay, it's like if you take a paper and just twist it a little bit, that's what I'm talking about. So what we have to do in that case is, of course, we have to come up with some procedure for approximating that. And generally what now I should mention that there are very rare cases where a mesh generator will actually give you 4 points that are not on a plane. Okay, generally they are, but you have to always look out for exceptions when you process such information. So the way this is typically done is you break up the quadrilateral into 2 triangles. Okay, and then you compute the area of each triangle, and then finally add it up to get the area of the quadrilateral. That's of course an approximation, but if the 4 points are already on a plane, then it's not an approximation, it's the exact area. Okay, so that's the idea we use. So the area, this is something you know from your early studies in mathematics, probably late high school, where we know that the area of a triangle is given by basically the cross product of the 2 tangent vectors. Okay, T1 and T2 as I've denoted here. Okay, now note that those are not unit tangents, they are the actual tangents. Okay, and you take the half of that, and that gives you the area. So if I expand that out now, so this guy here, the cross product, so this is the magnitude of the cross product. The vertical lines are basically saying it's the magnitude. Okay, so what you have here is the cross product of 2 vectors. You have I, j, k, and then you have T1 x, T1 y, T1 z, and then T2 x, T2 y, T2 z. You take that determinant basically. So you have I times this minus that. Okay, and then negative j, because the sign goes -1 to the power I plus j. Okay, So then negative j times this minus that, and so on. Okay, and then k times this, or sorry, this minus that. Okay, that's what these terms are showing basically. And then you square and add them because you're calculating the magnitude, and then finally take the square root. Okay, so that's your area for one of the triangles. Okay, how do you code it up? Well, again, same thing. You're looping over all the faces. Okay, you're getting the indices of vertex 1, vertex 2, vertex 4. That's this, this, this. From the connectivity information, the same one that I showed you in 2D. You are asking for 1, 2, and 4. Okay, assuming that you know already this is a quadrilateral. Okay, in general, you would do some check to see what kind of topology it has to begin with, whether it's a triangle or a quadrilateral. And then you're calculating the T1x, T2x, T1y, T2y, T1z, T2z, the tangent components, and then this is finally your area. Okay, and the total area of the triangle is that divided by 2. Okay, and then you repeat that for the next triangle. All you do is you replace this statement in your code, that V1, instead of using number 1 here, you're going to use 3. Okay, so you replace that by that and then do the same calculation. Only one line change in the code. Okay, the vertices 2 and 4 remain the same. And then you repeat that. So you can just call V1 equal to L face to node of IFC comma 3. That's all. All right, and then repeat the calculation and then finally add the two areas. Any questions on that? So this is just straightforward application of concepts we know from elementary geometry. All right, now let's talk about surface normals. So calculation of surface normals in 2D, again we are looking at essentially an edge and a surface normal to that edge. Okay, now most mesh generators will already give you that, as I mentioned in the last class, and they will generally point the surface normal from cell 1 to cell 2. Okay, whichever one they are calling 1 and 2. But let's say they don't give you the surface normal information, then you have to compute it. So how do you compute it? You simply again use geometry. These two constraints you satisfy. One is that n dot t must be 0, t being the tangent, and n cross t should give you the k vector. Okay, why? Because the 2D mesh is usually on an xy plane. Almost all mesh generators that you have out there will generate a 2D mesh on xy plane. Okay, so what you're doing there is you're saying, okay, here's my n vector, okay, and here's my t vector. I do n cross t, that gives me a vector pointing outwards. Okay, that's the k vector, the z direction. So it's a right-handed coordinate system. You're basically applying a screw rule, which you go this way, and then that gives you a vector which is pointing outwards from the plane. All right, so if we expand that out, it's very simple. Again, we are doing n dot k, n dot t. So I showed you this before. That's the structure. So that becomes equal to k. Okay, so therefore this quantity must be equal to 1, and so we get that equal to 1. Okay, and now if I solve this equation and that equation, you get that. Okay, now again, this is something, you know, we are taught at the high school level, where we say, okay, if I have a line and I want to calculate the perpendicular of the line, you exchange the y and x and y components, and then you make one of them negative. Okay, that's what this is happening. You've exchanged the x and y components. As you can see, the ny has a tx and the nx has a ty, and then one of them is negative. Okay, and then the tx, the tangents, this is very straightforward. Again, all you do is this coordinate minus that coordinate, and then divided by the magnitude of that vector. That gives you the unit tangent. Remember, these are unit tangents here. Okay, otherwise this cross product will not give you k. It will give you some scalar times k. Okay, it's not going to give you a unit vector. Any questions? All right. So here is a sample code to do that. Okay. So again, we are getting vertex 1, vertex 2. Here's my tx, ty. Note that I've divided it by the area. Why? Because the area is nothing but this guy that I have in the denominator. Area being the length of that segment, really. Okay. So if I have already calculated the area of the face, that's nothing but the length of that segment. Okay, and I'm simply dividing by that. And then your two normals, and then you store them in slots 1 and 2 of your surface normal at the face. Okay. Any questions? All right. Let's talk about 3D now. Surface normal in 3D. And as I mentioned, if you have 4 points on a surface, then they're not guaranteed to have a unique surface normal. Okay, so what you have to do, what people usually do is, again, they break it up into triangles. They calculate the surface normal of each triangle, and then they use the average value of that surface normal as the surface normal of the quadrilateral. Okay, for lack of better alternatives, really. So again, we split that up into 2 parts. Okay. And so, for example, I want to calculate the surface normal here, pointing outwards. Okay, that's going to be the cross product. And once I compute this guy n, remember again, these two are not unit vectors. So this vector here is not going to be a unit vector. So therefore, I need to divide by its magnitude to compute the unit vector. Okay. So same idea, you calculate your n and then you divide by the surface normal. So again, get your 4 vertices. Okay, here are your 4 tangents, or 2 tangents. Now a lot of this is repetition. As you can see, this is what I'm showing you here is what I had shown you earlier when we calculated the area. So really you can calculate the surface normal and the area in the same loop. You shouldn't be repeating it. Okay, because all this stuff is the same as, remember, area was just cross product of these 2 vectors, half of that. Okay, so we are calculating those 2 vectors again, or I'm showing it here again, but you really don't need to repeat it for calculating of surface normal. You do it in the same loop. Okay, and then this is your nx, ny, and z, which is basically this calculation here. And then here is the magnitude of that. And then finally what I've done is I've taken each component, divided it by the magnitude. Okay, this is actually the magnitude squared, and stored it in slots 1, 2, and 3. Okay. Now, of course, you need additional logic to figure out which way the surface normal is pointing, whether it's into the control volume, out of the control volume, and those kinds of things. But we've talked about that before already. Okay. Any questions? All right. Let's talk about volume, calculation of volume. So we've talked area and surface normal. Now we're getting to the third piece, volume. Volume in 2D is the same as area in 3D. Okay. So that formula that we used, 1/2 times the cross product of the 2 tangents, that's applicable to calculating 2D volumes. Okay, we can do that. But there's a better way of doing that, and that uses the Gauss divergence theorem, and this can in fact be applied to both 2D and 3D, and this is what people usually do. Okay, it's really a neat method, as you will see. So Gauss divergence theorem, we've talked about this many times by now. This is what the theorem says. So it says if I have divergence of a vector and I do a volume integral over some volume V0, then it reduces to the surface integral of q dot n dA. Okay, and this is the geometric interpretation. Now suppose, so I'm going to use this theorem to calculate volume of an arbitrary polygon. Okay. Let's say we assume a vector, so this q vector, let's say we call that x times I. I is my unit vector in the x direction, and x is just a scalar quantity. All right. So if I do divergence of q, then that's divergence of x times I. Divergence means I ddx plus j dy plus k ddz. I dot it with x times I. Okay. So therefore that gives me basically I dot I times differential of x, which is 1. Okay. So the answer to this is 1, because the j dot I and k dot I will give me 0. All right. So if my q is x times I, then the divergence of q is 1. All right. So I can now use that and arbitrarily insert it here. Okay. So I can say that volume of a control volume, which is integral over v naught dv, is nothing but integral over v naught divergence of q dv. Why? Because divergence of q is 1. Okay, for the specific case when q is equal to x times I. So I'm arbitrarily inserting it into this integral here. Okay, everybody follow that? All right, so now we are in a position to apply divergence theorem. So we have a divergence of a quantity inside a volume integral. So I can write that as a surface integral. Getting back to what my q is x times I. So it becomes a surface integral of this quantity. Okay. So if I now expand this surface integral, basically it becomes integral from 1 to 2, 2 to 3, 3 to 4. Okay, and so on. And then you'll have 4 to 1. So 4 integrals which have this as the integrand or the kernel. All right. So let's consider the integral from 1 to 2 xi dot n dA. Okay. So xi dot n is nothing but x times n12, the x component of that. Okay. The subscript 1, 2 is simply saying for the edge 1, 2, and the subscript x is saying it's the x component, because I dot n gives you the x component of the surface normal. Okay. So here is my surface normal n. This is n12. Okay. If I take n dot I is pointing this way. Okay. I get the x component of the surface normal, which is what this is. Similarly, if I do, well, so that's the only term we have here. So now this guy n122 or n12x, this component of the surface normal, is not changing when I go from 1 to 2. When I go from here to here, the direction of the surface normal is not changing. It's constant, because this is a polygonal face or polygonal control volume that's bounded by discrete straight faces. Okay, if it was bounded by curved surfaces, then yes, the surface normal would change at each point. But luckily, our mesh generators don't generate those kinds of control volumes. They generate polygons or polyhedrons, okay, which have straight faces or edges. So this surface normal is not changing when I'm going from 1 to 2. Therefore, I can pull it outside the integral. Okay, and my integral simply becomes from 1 to 2 x dA. Okay. Here's a little figure which now reduces that further. So basically I'm doing an integration over this length dl. Okay. So dA is nothing but dl, because this is 2D we are looking at. Okay. The area is nothing but length. And then the dl you can express in terms of x. It's simply dx over cosine theta, as you can see from that diagram. Okay. So that's what I've done here. I've changed the limits from, instead of from 0 to L, I've changed it from 0 to L cosine theta, which is from here to here. So I've basically done a coordinate transformation here to go from L to X. And then my dx is nothing but, or dl is nothing but dx over cosine theta. And then when I finally perform the integration, this is the result I get. Okay. So this L cosine theta over 2, which you have in this formula here. So I have L times L cosine theta over 2. L cosine theta over 2 is nothing but the x coordinate of the midpoint of that edge. Okay, here is up to here is your L cosine theta, this part here. Okay, this, the x coordinate there is L cosine theta over 2. All right, so this integration here is basically giving me L times the x coordinate of the midpoint, okay, of that edge. So therefore, this simply becomes, this one I already had, I had pulled it out. I have area 1 to 2, which is nothing but this L itself. Okay, that's the area of that segment. And then I have x 1 to 2, which is the x coordinate of that segment 1 to 2. Okay, everybody got that? So if I extend that to all 4 edges now, then I have a summation over, or basically 4 integrals, and I can write that as a summation over faces nxf, which is basically that guy. Okay, the x component of the surface normal at a face, the midpoint, the x coordinate of the midpoint of that face, times the area of the face. Okay, now it turns out that, I mean, I kind of went through an example here, but it's pretty easy to show that you can do this integration in general, and this is the result you will always get, whether it's 2D or 3D. All right, because essentially what we are doing here is we are calculating the average of a linear function, which is always at the midpoint. All right, so that's what you end up getting. So your volume, okay, as I have shown here, becomes that. Okay, now this expression that I derived was with the, we made the assumption that our vector q is x times I. Okay, I could have done the same derivation, okay, I'll get to the code in a moment, using q is equal to y times j and or q equal to z times k. Perfectly valid also, you know, to take any of those as your q. If you did that, if you use this expression, then you would get an expression which would look like that. Okay, where it would be the y component of the surface normal times the midpoint, the y coordinate of the midpoint, and here if you do this, you will get the z component of the surface normal and then the z of the midpoint. Okay, now what people usually do is they take, so if I call this v0 x and this one v0 y and this one v0 z, they're supposed to be the same. Okay, ideally the mathematics is exact, so those answers should come out to be the same, but sometimes due to numerical precision, suppose a cell is very skewed, obtuse angles or very acute angles, they may not come out exactly the same. Okay, those 3 answers. So to avoid any kind of precision related problems, people usually take 1/3 of the 3 volumes in 3D. Okay, in 2D you will just do 2 of them. Okay, that's just to avoid any kind of numerical precision errors. But in principle, those 3 answers should be the same if you do it 3 different ways. Okay, here's a little code for calculating the volume, this formula here. Okay, so what are we doing here? So I'm looping over all cells, so I want to calculate the volume of all cells in my computational domain. Okay, so I'm looping over all cells. From the cell index, I'm getting how many faces does this cell have, or that control volume have. That's the first thing I get. Then I'm setting the volume of that control volume to 0. I'm initializing it to 0. Okay, then I'm running a loop over all the faces. From the face, local face index, remember this is local face index going from 1 to, so for a triangle it will go 1 through 3. Okay, so this face index will run 1 up to 3 for a triangle. So what it's doing is it's taking the local face index. From the local face index, it's getting the global face index. Okay. Once it has the global face index, we have already calculated and stored these guys, face coordinates, areas, surface normals, and so on. We're just using them. Okay. This guy here, as my note says here, makes sure that the surface normal is pointing outwards always from that control volume. Okay, remember we applied the divergence theorem to derive this formula. The divergence theorem assumes or presumes that the surface normals are all pointing outwards in the control volume. Okay. So that's all this is doing. It's just getting that global face index. Once you have that, you use your surface normal, x coordinate of the face center, and then the area to do that summation. Okay. Add it up, and that's your volume of each control volume. Okay. So this, by the way this is being done, it's applicable to any control volume shape. It doesn't have to be triangles, quadrilaterals, polygons, whatever shape, doesn't matter. Okay. This is a general summation over all the faces, and it is also applicable to 3D. Okay. You don't have to do anything special for 2D versus 3D. All right. Any questions? Now, the only caveat is that it's applicable, this method is applicable only to control volumes or cells that are bounded by straight-edged discrete faces. Okay. Okay, so that's your volume calculation. Another quantity we often need, and this is something that you will see when we actually get to the finite volume formulation, is this quantity called delta. Okay, this delta is if I take two cells, suppose 1 and 2. Okay, I've numbered them, and I draw a vector joining the two cell centers. Okay, that's the vector L in green. So if I take n dot L, okay, you can see that n dot L is nothing but this distance. It's the distance normal to that face between the two cells, okay, between cell centers 1 and 2. So it's the component of the L vector in the direction of the surface normal. All right, which I've marked by delta here, and you will see when we do the finite volume formulation that this quantity always shows up in the finite volume formulation. Okay, so therefore what people do is they calculate and pre-calculate and store this quantity, n dot L. Okay. So to compute that, all you do is you execute something like this. So again, what we are doing is we are looping over all faces. We want to calculate this quantity for all faces. Okay. So we are looping over all faces from the face and the face to cell connectivity information. We are getting the two indices of cell 1 and cell 2. Those are the two global indices of cell 1 and cell 2. Okay. We are checking to see if it's an interior face or not, because if it's a boundary face, then one of them doesn't exist. You have to do something different if it's a boundary face. Okay, because cell 1 and cell 2 both don't exist, only one of them do. All right. So if it's not a boundary face, if it's an interior face, okay, I think I've labeled this wrong. Let's see. This should be a 0 here. Okay. So interior faces would typically mean B face equal to 0. That means it's not a boundary face. All right. So my comments are correct, but this should typically be a 0 here. So what it is then doing is it's calculating the L vector. So you can see I'm calling it vec L. Okay. So these are the three components. It's simply subtracting out the coordinates. Okay. So it's the coordinates of 2 minus coordinates of 1, or position vector 2 minus position vector 1. Okay. So that's your vec L, and if it's a boundary face, instead what it does is, so suppose this becomes a boundary now. Okay. Then it's going to take the face center, wherever that is, minus the cell center. Okay. So it's now going to calculate the normal distance up to here. That will become your delta. if it's a boundary face. Yeah.
That delta, that's a projection, right?
Yes. Yeah. So that delta is, think of it as the distance in the direction of the surface normal between cell 1 and cell 2. Okay, so we calculate the L, and then here is your actual delta. So what you see here is we are dotting it with the surface normal. This is a direct dot product, as you can see. Okay. And then we are taking the absolute value because the surface normal may be either pointing from cell 1 to cell 2 or cell 2 to cell 1. We don't know a priori. Okay. So instead of checking for the sign of the surface normal, we know that, okay, we want to just store the distance. So we're simply taking the absolute value of that dot product. Okay. Any questions there? All right. So I think we are done with all the geometric quantities. Just summarizing, we have everything at our disposal. We have areas, volumes, surface normals, normal distance, all these things we talked about today, and then previous class we talked about the fact that we have all the connectivity information, and we also have what else? The interpolation functions to get face values from cell values or vertex values from cell values. Okay, so all those things by this time are at our fingertips. We have written a code which pre-processes and stores all this information. Okay, so now all we are going to do is, okay, once we do the finite volume integration, how do we use all this information to basically develop a discrete equation that we finally want to solve? Okay. So here is our governing equation. Let's say, again, we are taking the Poisson equation as an example. It doesn't have to be, but that's what we've been dealing with, so we'll stick to that. Okay. So as I showed you maybe 3 lectures ago when I first introduced you to the finite volume equation, once you apply the divergence theorem, this is what you end up getting. Okay, so you're going to start with an integration of this guy on both sides. Okay, then this guy, the left-hand side, will simply become a surface integral of gamma grad phi dotted with n dA, and then the right-hand side will simply become S naught times V naught. Okay. So this guy then is represented by a summation over the discrete faces of the control volume. Okay, so this is the general finite volume equation that we always start with. It doesn't have any approximations whatsoever other than the fact that the faces are discrete straight faces. They're not curved faces. Okay. But no approximations in terms of what shape control volume or how many dimensions, 2D or 3D, okay, or how many faces the control volume has, any of that. Okay, so we're starting from that. And I showed you in the previous lecture, you know, for example, when we looked at a Cartesian mesh like that, we said, okay, we break it up into east, west, north, south, and then on the east face, my n is I, on the west face, it's minus I, on the north face, it's j, south face is minus j, and so on, and then we reduced all these expressions, and AF was either delta x or delta y, and then we got the equation that we are familiar with for a Cartesian grid. Okay, here we are not going to bother with that, and we're going to move on to the general case. So I'm going to start everything from an unstructured mesh right away. Okay. So those star marks 1, 2, 3 are the face centers. The blue circles are the cell centers. Okay, and we are labeling them not 1, 2, and 3. So this is what we start with. First thing we have to calculate in this formula are the face values of gamma. What do? We do an interpolation. We already know this. All these weight functions are known. So you can calculate the gamma f. Okay. So suppose you want to assemble your matrix for the finite volume method. You've done all the grid processing, all the geometric processing. Then probably the next step would be to call a function which will calculate out the gamma f for each face. Okay, because you know I'm going to need that in the finite volume formulation. Okay, so rather than do it locally on the fly, I'm just going to calculate it in a function and store it. Okay, so I can just use it later on. So that's what you would do. Okay, and I've shown you this example. All you have to do is write a function which does this. That's all. Okay, takes the gamma values of the two cells next to the face and then adds it up with that weighting function. Okay, next task. So we are going stepwise. We are finished with this. Next task is how do we approximate that? Area of face we already know, so that's not a problem. Okay. So this guy, so in our finite volume formulation, if you go back and think about your Cartesian mesh, this guy here became, on the eastern face, for example, it became, well, I should write partial derivatives, d phi dx at the eastern face. Okay, and then we did Taylor series expansions, and it became phi east minus phi naught divided by delta x. That's what it became. Okay, so in other words, what we're trying to do is we are trying to write this in terms of nodal values or cell center values. Okay, that's our objective. So let's talk a little bit about what happens with this quantity. So first of all, gradient of phi is that ddx I, ddy j, ddz k. I already mentioned this, that gradient of any scalar is a vector. Okay, has three components. I, j, k are unit vectors orthogonal to each other. So these are, we are taking the Cartesian unit vectors, I, j, and k. Okay. Now, you don't necessarily have to write a gradient in terms of these unit vectors. You can use any three other unit vectors, okay, as long as you have an independent coordinate system which has three independent directions. All right. So for example, I could write this as d phi dx times e1 plus d phi d, or d phi d e1 times unit vector e1 plus d phi d e2 unit vector phi 2, and so on. Okay, some arbitrary coordinate system. One way to write this would be to use the local normal and the two local tangents. That's also a Cartesian system. It's just not aligned to x, y, z. So if I, take a surface, I have a normal and I have two tangents. Okay, those three unit vectors can be deemed a local coordinate system, and you can write a gradient using those three unit vectors. Okay, it doesn't have to be your x, y, z unit vectors. Okay, so in general, you could always write this using two tangents and a normal. Okay, now the catch here, of course, is that the normal and the two tangents must be orthogonal to each other to be able to write it that way. Okay, now whether that is always the case or not, we'll defer that discussion until later. Okay, another thing to understand is that d phi dx, this guy, can be written as grad phi dot I. See, here's your grad phi. If I dot it with I, okay, what do I get? I get I dot I, which gives me a 1 and a d phi dx in front. Then I get j dot I, which is a 0, and a k dot I, which is a 0. So the d phi dy and d phi dz go away, and I'm left with d phi dx. That's another way of writing each of the components like that. So therefore, I can write my grad phi as, this is my d phi dx, so grad phi dot I times I, grad phi dot j times j, grad phi dot k times k. Okay? Just a different way of writing the expression that I have here. Right? Everybody got that? Similarly, if I use now my local coordinate system comprised of two tangents and a normal, I can write it this way. Instead of ijk, I'm using n t1, t2. Okay? Now let's consider a 2D system. In a 2D system, you don't have two tangents. You have, in Cartesian coordinates, you will have just I and j, no k. Okay? If you use the local coordinate system, you will just have n and t. There are no two tangents. It's just one tangent. Okay? The tangent is this way, and the normal is that way. Okay, that's your local coordinate system, a normal and a tangent vector. Okay, so therefore I can write my gradient at the face at that point as gradient at the face dot the surface normal at the face times NF and then tangent times TF. Okay. Now we are going to consider this L vector, which is joining 0 and 1, the two cell centers. Okay, and I'm going to take this equation and dot it with that vector L. Okay, so here is one vector. Gradient of a scalar is a vector. We can see that clearly. I'm going to dot it with the L vector. Okay, so both sides. So I'm doing that dot L here also dot L dot L. Okay. NF dot L is what we called delta earlier on. Remember, this is something we pre-processed and stored. That shows up here. Okay, so we're going to replace that by delta. All right, and then the second term we are going to just leave it as is for now. Okay. So now let's consider this guy, the left-hand side of the equation that we just derived. Okay, so this guy. What is this grad phi f dot L? So what we are going to do is we are going to do a Taylor series expansion of f about 0 and f about 1. Okay, so f about this guy and f about that guy. So these are the two Taylor series expansions. So we are saying, or sorry, the other way around. Phi 1 in terms of phi f, okay. So that's d phi dx at f, x1 minus xf plus d phi dy. Remember, now it's a two-dimensional Taylor series expansion because, you know, there's a delta x between these two and then there's also a delta y between those two. Okay. As opposed to what you had in a Cartesian mesh where when we derived d square phi dx square, we only thought about the x Taylor series expansion because the lines were orthogonal to each other. Okay, but here you now have a two-dimensional Taylor series expansion. These are the first two linear terms. Then you have the second derivatives. Okay, and then you start getting cross derivatives too. Okay, same thing for phi naught. We subtract one from the other, we get this. Okay. Now, what is this right-hand side? Now, of course, you know, this is an approximation because we have thrown away the higher order terms. So we've truncated the Taylor series right there. Okay. Now, this is nothing but, if you start thinking about it, x1 minus x0 and y1 minus y0. What is that? That's the L vector. So all we have here is grad phi f dot L. Okay. Because grad phi f is dx, d phi dx I plus d phi dy j, and then we have dotted it with the L vector, which is x1 minus x0 I plus y1 minus y0 j. Okay, so this is your phi 1 minus phi 0, approximately at least. Okay, disregarding the truncation errors in your Taylor series expansion or the higher order terms in your Taylor series expansion. Okay, so that then becomes one of the questions. What is the error in this approximation? Okay, so phi 1 minus phi 0, we have approximated it as that, and of course now we are going to get some error. What is that error? That error is all those higher order terms that we threw out. It has, you know, these kinds of terms if you go back to the expression on the previous page. Okay. Now, if I look at that, it's very hard for me to say, is that first order, is that second order, what is it? Okay. You don't clearly see a delta x, delta y kind of thing here. All right. One way to assess it further or examine it further is to say, okay, here is my error. Okay. And of course, like I said here, it has units of length square, while the denominator has units of length. So you can see here there's a square here of length square, and then the denominator, this has units of length. So it would appear that the error is first order because I have a length square divided by length. Okay? But let's examine that a little bit more. If we make the approximation that y1 is equal to y0 is equal to yf, in other words, I have a mesh which looks like this. It would be still unstructured, but two control volumes which look like that. Okay? So the y coordinates of the two cell centers are the same. Only the x coordinates are different. Okay? If I take that limiting case, then my error reduces to that. All the terms go away. I'm just left with that term. Okay, because you can see here, this y1 minus yf, y0 minus yf, all these terms will go to 0 because yf is right here. That also has the same y coordinate. Okay, so we get that, and we can write this as, so what I've done here is this is like a square minus b square. So I can write this as a minus b and times a plus b. Okay, and when I simplify, I can cancel out these guys, and I'm left with that. That's the error in my approximation. Okay. Another way of writing that is this way: x1 minus xf minus xf minus x0. Okay. So what are we saying? If I now start thinking about this, let's call this delta x1, and let's call this delta x0. Here is my node 0, here is my node 1. So this is nothing but delta x1 minus delta x0. Okay. So that's the error in my approximation. So the error is not really proportional to the distance itself, delta x, but it's proportional to the differences in the distance. Okay, so this is the leading order error term, remember. Okay, so now we are trying to answer the question, what is the order of my scheme? When I go from, when I replace this guy, this is, remember, an exact differential quantity. I'm replacing that by an algebraic approximation, right? This is just like what you did for your finite difference or finite volume. You had d phi dx, you wrote it as phi east minus phi naught divided by delta x. Okay, so a differential operator became an algebraic equivalent. Same thing here. This is a differential operator. Okay, you're replacing it by an algebraic equivalent. So the question we are asking is, what is the truncation error or the discretization error by doing that? All right, and here what I'm trying to show you is that you can show that in the limiting case, that error is of this form. That's the leading order error, though. There are other higher order terms. Okay, so what this is telling me is that if the mesh is equal sized, okay, or all these triangles are of equal size, then this error is going to disappear because obviously this distance is going to be the same as that distance if they're all equal sized triangles. Doesn't matter that it's an unstructured mesh. Okay, it's exactly the same as what you had in your Cartesian mesh formulation. If we have equal sized mesh, this truncation error, this leading order term actually vanishes and you get second order accuracy. Okay, here what we are finding is that, in fact, if you do the derivation for, I had asked you probably in lecture 1 or lecture 2 that derive the error expression for an unequal sized mesh. Okay, and we ran into the same kind of situation that the leading order error term actually has a difference between two delta x's, and if those two delta x's are equal, then that term vanishes and we are back to second order scheme. So the same thing happens with an unstructured mesh. You get somewhere between first and second order. This is closer to second order if the rate of stretching of the mesh is mild. Okay, if the rate of stretching of the mesh is very high, then these two quantities will be very different. So suppose I have a triangle like that next to another triangle like that. okay, then that rate of stretching is very high. And so what happens is delta x1 and delta x0 are very different. So the difference will be significant and you'll get first order error. Okay. On the other hand, if you stretch your mesh gradually and these two triangles are almost the same size, maybe they are different by 5%. Okay. Then these two quantities will be very similar and you will still have that leading order error term, but it will be multiplied by a very small value in front. Okay. Everybody get that? All right, so getting back to our formulation. So this is just examination of the kind of error we introduce, okay? And it's very similar to what we see for Cartesian meshes, which is to be expected, okay? So now we are back to this expression here. So we can say that this is of order approximately, delta x to the power n, where n is somewhere between 2 and 1. It is closer to 2 if the stretching ratio is high. If it's closer to, or 1 if the stretching ratio is high. It's closer to 2 if the stretching ratio is small. Okay. All right. So that's your error. Getting back to your formulation. So here is what we had. So we were here. We were trying to approximate this. Now we have done that. That's your approximation. Okay, so we are going to plug it into this expression. This goes in here and we rearrange so we can write this quantity as that. All right. So my finite volume expression, instead of going back to the previous slide, I'm just going to write it out here. We had gamma f grad phi f dot nf af is equal to s naught v naught. That was our finite volume equation. This guy we know how to get, interpolation. Area we know. This guy now gets replaced by this expression. Okay, so we have essentially phi 1 minus phi naught over delta plus this additional term which shows up. Okay, we are going to talk about that additional term in the next class, but there are a couple of things I want to point out. If your NF and L are co-aligned, that is, this vector is co-aligned with the surface normal, okay, then TF dot L is automatically 0 because tangent will then be perpendicular to L. All right. In that case, you can see here I have a TF dot L. That last term will vanish. Okay. So what you are going to get in the end is you're simply going to replace this term here, this whole term here, by phi 1 minus phi naught over delta. Okay. That is exactly the same equation that you had for a Cartesian mesh, which had a gamma at the face times phi east minus phi naught over delta x. Okay. So identical expression we are getting here if these two vectors are co-aligned, NF and LF. Okay. Now one common misconception that people have, let me just draw a figure here. If you start thinking about when can NF and LF be co-aligned, or NF and L, okay, when can those two vectors be co-aligned? The common misconception or common thought is that people think that, okay, Cartesian mesh, obviously they're co-aligned. Okay, so here are two cells, here is my L vector, and here is my N vector. So obviously they are co-aligned. Okay, and then the extrapolation to that is people think that's the only case where it's co-aligned. Okay, you've got to have a perfectly Cartesian mesh, otherwise they are not going to be co-aligned. Wrong. Okay, and this is what the finite element people really, they kind of capitalize upon is the fact that if you, let's say, take your square that you've been modeling so far, and instead of a Cartesian mesh, you fill it up with equilateral triangles, okay, you're going to get the exact same thing. By definition, all the surface normals and the L vectors will be co-aligned. Okay? So just because it's a triangular mesh doesn't mean that your normal and L vector will not be co-aligned. If they're equilateral triangles, they will be. In fact, all the great mesh generation algorithms, for example, Delaunay triangulation, they want to enforce that as much as possible. Make triangles with 60-degree angles all the time. Okay. Same thing in 3D. If you have tetrahedrons which are equisized, you know, all the triangular faces of the tetrahedron of same area, you will get again the same thing. Normal and tangent co-aligned. Okay. Now, I'm saying all this. The real issue is, why do we want them co-aligned? Okay. Well, we want them co-aligned because here's what's happening. What we have done here is we have taken a vector, okay, and we have decomposed it into two parts. One that is joining the vector between the cell centers, and another one, this guy here, is sort of like a tangential component of that vector. Okay, we often call this the tangential flux. So we've basically decomposed the flux into a normal flux and a tangential flux. Okay, later on in the next class, I'll show you that the treatment of this is done explicitly. So what happens is, once you write your discretized equation, you take that term and throw it over to the right hand side. It's kind of like your Gauss-Seidel scheme, where out of, you know, out of 5 terms, 4 of them you treat explicitly and throw them over to the right hand side. Same thing here. You can take this term, throw it over to the right hand side, and then solve your equations. Okay. Now what will that do? Obviously it will slow down your convergence. You've added more explicitness to your equation. Okay. So the smaller that term, the better off you are in terms of convergence. Okay. And where does that lead us? That leads us to, you know, right to the basics, that if you have a bad mesh, you'll get poor convergence. Because that term will be treated explicitly, it will slow down your convergence. There are very few codes in this world where that term is treated implicitly, because if you actually try to write it implicitly, you'll see that you have to extend your stencil. It becomes pretty difficult, at least in a finite volume or finite difference formulation. Okay, so that's the reason, you know, it all goes back to your mesh generator in the end. If your mesh generator is producing a bad mesh, you'll get poor convergence. As a user, you are much better off spending a lot of time getting a good mesh, you know, spend a couple of days getting a good mesh and then running your cases, rather than having a poor mesh and your code taking days and days to converge, and sometimes convergence stalling. Okay? Even though it's tedious and it's really something we don't like to do, spending too much time on mesh generation, but that's the way it is. Okay? And most mesh generators now give you a lot of information on basically it gives you statistics on the type, on the angles essentially. Okay, so if you look at the histograms they plot, so they'll have, typically it'll look like this. Okay, so this is angle theta, and this is, you know, of course, number of cells. So it'll look like that. And for hexahedral meshes or quadrilateral meshes, you should see a clustering around 90 degrees. Okay? In other words, you don't want quadrilaterals which look like this. That's bad. This is way out of whack, these kinds of obtuse angles or these kinds of acute angles. Okay? They are in the fringes of this histogram. All right? So you want clustering around 90 degrees if it's quadrilateral in 2D or hexahedral in 3D. Okay? If you are now looking at triangular or tetrahedral meshes, they should be clustered around 60 degrees. Okay? If it's all 60 degrees, then that's great. That means you have no explicitness in your calculation. It's perfectly implicit. Okay? So keep that in mind, that when you guys generate meshes and do these kinds of calculations, ultimately the mesh quality will severely affect your convergence. Okay, so you don't want to have mesh that have these large populations at the fringes. Okay, they should be clustered around 60 degrees or 90 degrees.